drinking. It just means that someone do that.
Good afternoon, Professor.
Afternoon.
Thank you, sure. Thanks. Yeah, already that, but like, you guys speaking about. Sir. Yeah, because of what I'm so bad.
Initial reports and just.
The hospital has something. I guess it's pretty. Yeah. I'm looking for them. Like more. I agree. That's me. The second one is so. I think like political class there is the vice versa. Cool one. Let's see. Who does their? It is the rest of that. Usually there's. How about the sheet? But it's not true. I because that's really high. You might blow. I just think so. Yeah. So like constant, not true false. If you have a state one, and he doesn't shut it, but you see it. Hey, somewhere Chase, I'm like, I go. You down. Yeah, you got that.
Recording in progress.
Okay. Guys, we're gonna get started. like I said last week, last time, we're going to cover more examples before we conclude the chapter. Just from the different angles to look at different problems and show you guys what is the best like procedure to handle the problem, to how to get it started, and how to verify your answers, things like that. So yesterday we went through 6.5. Basically, we're looking at two different scenarios. The first scenario is looking at one operating mode, and then the second scenario, we're looking at just started with the assumption saying it's in active mode, but we found that it's not possible because if you do that, the voltage at the collector is actually less than the voltage at the emitter, which is impossible. So therefore, we have to redo the calculation and find out, yeah, actually it is in the saturation mode, and our first beta is small instead of big one. So that shows you how the process can get sometimes, you got the right assumption, then you finish the problem. But if you got the wrong assumption, you verified it's not right, and you got to redo the problem with another assumption. Most of the time, you will get a problem which is either in saturation or in active mode. But sometimes we might also ask you to look at whether the circuit is actually in conduction or it's in off mode. Because transistors, MOSFET and BJTs, they all have three different modes. For MOSFET, there's off, there's a triode, there's a saturation region. And for BJT, there's off mode, there's a saturation region, and there's an active or linear region. So you have to understand all three different operation modes. In this example, it is asking you to save the voltage and current in each branch. So by looking at the circuit, you see what happened is the emitter is grounded and the base is also grounded. So here, if you just look at little loop, what voltage do you have from base to emitter? From base to emitter, how much voltage do you have? I mean, even though there's a resistance there, but you're from ground to ground. So you really have zero. So if we be zero, we know that this thing is going to be in off mode. There's nothing else you need to do after this. But of course, it was asking for all the currents and the voltage in branches. You don't forget, it's just saying off mode. But actually, if we're using off mode, all the currents, IB, IC, and IE, they're all going to be zero. So that's something you can write right away. But also, there's one more thing, just look at the voltage. VC and VE. Of course, VB, it's grounded, so VB is zero, and VE is also zero. So those are very easy to find. Right? About the collector. The collector is connected to the 10 volts, and there's no current either in that branch. So the voltage drop on that resistor RC is also zero, and therefore your voltage VC is 10 volts minus I times RC, and it equals to 10 volts. So just, I know, like, of course, we do exam in multiple choice, but in the previous exams, and students saying, oh, it's off, and then just didn't do the rest of the voltage and currents, and you lose half of the points because what it's asking you is to find the voltage and current in the circuit. It didn't ask you whether it's off, whether it's on. So just be careful for what you're doing. Okay. So now we switch gear to look at a PNP MOSFET. So if you look at the arrows at this point, you know that this is a PNP. With the PNP, we draw the emitter on top and the collector at the bottom. And the current flows from, if it's on, current would flow from emitter and split between base and the collector. So that's how a PNP works. So in this circuit, some of the parameters are given. The voltage, this is a -10, and that's ground. So, yeah, go ahead.
I was just on the previous question,
Yeah,
if the voltage goes from 10 volts up top to 0, like would there not be a current flowing? No.
if the, okay, can you elaborate your question?
At the top, we have 10 volts.
Yeah.
And then at the bottom, it's grounded to 0. So with the voltage drop, would there not be a current?
The voltage drop, oh, you mean there's a voltage drop VCE, right? Yeah. So there's a voltage drop VCE is equal to 10 volts. But there's no current. You can have a voltage, but you don't have to have a current to have a voltage. Because the base is grounded. You have to have a base more than 0.7 volts. Base to emitter. So base to emitter is 0 voltage. So that PN junction is not conducting, okay? So this is a PNP. So with a PNP, now maybe we look at one more step before we go next. In this example, we have ground. The voltage between base and emitter is 0. Therefore, it's not conducting. But in the next example, so apparently we also have the base grounded. But we do have a negative voltage at the bottom of the collector, and we do have a voltage at the emitter at the top. So therefore, this circuit is likely in conduction mode. Why? Well, because if it is off, you think if it is off, how much voltage is here at the base? 0, right? Grounded. And how much voltage at the emitter if it is off? Off means no current. Emitter will have voltage of how many volts? 10 volts. Now from emitter to base have 10 volts, that's not possible, right? So which means you rule out emitter to base. Okay, so now we have explained it's not off, so it must be on. So if it is on, well, we wouldn't know whether this is in saturation or whether it is in active mode. So how do we know that? Well, the only way to know is to do some assumption and solve the problem and then verify whether your assumption is right or not. If it's right, done. If it's not right, your assumption is wrong, redo it in another mode. So let's do it. So if we assume in active mode, okay? So we're gonna assume, if we assume in active, oh, there's one more thing you got to look at. It says assume beta is infinity. So when it assumes beta infinity, what really this tells you is IC is equal to IE and IB is 0 because IC is beta times IB, right? So beta is infinity means IB is 0. So 0 times infinity, that gives you a number. There's the same order. So, so in this case, if we assume in active mode, we will have here VBE. So we'll have VBE or VEB in this case. Let's call it VEB. Because of PNP, so it's going to be VEB. So VEB is going to be 0.7. That's what we derived from the assumption. And then if we have that, we'll know that this voltage here, VE, is going to be 0.7 volts. So why VE is 0.7? Because base is grounded. So if VB is 0.7, then VE must be 0.7, right? So if VE is 0.7, then we can find IE equal to 10 volts minus 0.7 divided by 2K. That gives you, that's 9.3, so 4.65 milliamps. And from the previous assumption, we know that IC are the same. So now we can say IC equal to IE equal to 4.65 milliamps. So the next point, we're going to find VC. So VC is going to be minus 15 plus RC times IC, right? So that gives you, so RC is 1K, so that gives you minus 15 plus 4.65 volts. That gives you minus 11.35 volts. So now we got the voltage of VC and we got the voltage of VE. So now we can find VE or VEC equal to VE minus VC. That gives you 0.7 minus 11.35 gives you 2.35. So this is larger than 0.3 volts. Therefore, our assumption was correct. Yes, correct. How do I? Oh, you mean this one?
Yeah.
Oh, negative 10. I'm sorry. Yeah, no. You're right. Sorry. Good catch. Yeah, no, you're right. So it shouldn't be 15. So I did it all wrong. Okay. Great. Thank you. Let's redo it. Okay. Good. So it's minus 10 plus RC times IC. That's going to be minus 10 plus 4.65. Okay, so this gives you minus 5.35. Okay, so minus 3.5 plus, no, this is going to be 0.7 minus 5.35. It gives you 6.05 volts. Well, still larger than 0.3 volts. Yeah. Thank you for that correction. So at this point, we're done with the problem. And we found that it is in active mode and everything works out just fine. But let's say if initially, you started with, so this is the solution we've already done, okay? Now, let's say initially you started assume it's in saturation. You know what's going to happen if you assume in saturation mode? So the way that you do this problem, of course, we have to redo it, but I just want to demonstrate, if you start with that assumption, it's nothing wrong by doing an assumption. It's just that by chance, it wasn't, right? So you just have to redo the problem. But let's say you start saying, because I think saturation is easier, so I want to start with the assumption in saturation. So if it let me redraw the circuit. Minus 10, 2K, 1K ground. So if I assume it's in saturation, I would have VEC equal to 0.2 volts. Right? That if you start at that assumption, you right away you get okay. Well, it's in saturation, the voltage drop between E and C is going to be 0.2 volts, and then we can find current IC equal to IE because battery is infinity. It's going to be 10 minus 10 divided by or minus 0.2 and then divide by 3K. So that'll give you 19.8, right? Divided by 3. So that's almost 6.9. Let's assume it's 6.9. It won't give you a big mistake here. So 6.9 milliamps. So now I can find VC equal to 10 volts minus, let's start with VE. VE is 10 minus 2K times IE. So that gives you 10 minus 2K times 6.9. That gives you 13.8. 13.8, that gives you 6.2 volts. Now we can find VC, it's going to be minus 10 plus 1K times, no, 6.9, no, I'm sorry, this is 2 times 6.9 is going to be minus 3.8 volts. Okay, because the 2 times 6.9, and then VC is 1K times IC. VC is going to be minus 10 plus 6.9. That gives you minus 3.1 volts. So VE actually less than VC. So we'll say assumption wrong. What I did is I find VE and I find VC. Now I find VE is less than VC. So which means this is not going to happen. VE is on top. It has to be higher than VC. So it's impossible. Therefore, our assumption is wrong. So if you did it like this, at this point, you say, okay, that's wrong. I'm going to have to go back to assume it's active and redo the problem. It just happened that way, so nothing wrong or right just by doing that. Okay. The next problem is about again, determining the voltage and current at each node. But of course, here it says better is equal to 100 instead of 20. So looking at this problem, certainly it wouldn't be in off mode. The reason that if it is off, if it is off, you would have 5 volts at base, right? Because if the voltage drop to 100K is 0, therefore you would have base at 5 volts. And you cannot have 5 volts from base to emitter. So therefore, this is not off mode. It has to be in either active or saturation mode. So not off, I would say. Just by doing that observation, you can find that. Now, if it's not off, we wouldn't know whether it's active or whether it's saturation. Therefore, we would have to start with one assumption. So let's do this problem. What do you guys like to do? You want to start with assumption, saturation, or linear? Active? Okay, let's start with active. If we start with active, let's say, okay, so VBE is 0.7. We can start with that. The VBE 0.7 means we can calculate IB 5 minus 0.7 divided by 100K. That gives you 4.043 milliamps. So that's something you can find a way. You look at the base to emitter because it's in a on mode, so therefore that's 0.7, 5 volts, 0.7, rest is dropped on the 100K resistance, right? So now you have 4.3 divided by 100, 0.03 milliamps. Now beta is given, so we can find IC equal to beta times IB. And the beta is 100, so therefore you get 4.3 milliamps. Let's directly multiply 0.043 by 100. So now we can do is to find VC. Now you guys use the loop analysis, you'll find, okay, VC simply is 10 volts minus IC times RC. That gives you 10 minus IC is 4.3 times 2, so 8.6. So it's 1.4 volts. So therefore VCE is VC minus VE is VC is 1.4 minus 0. That gives you 1.4 volts, which is larger than 0.3 volts, which means our assumption is correct. Now, at this step, you have one more current to solve, which is IE. So IE equal to IB plus IC. So that gives you 4.343 milliamps. Yes.
Sorry, could you why we know that it's an off mode?
Why?
Yeah, like set.
Or why is it not in off mode?
Yeah,
Because if it is off, you would have VBE at 5 volts. Do you see? If there's no current, right? And if there's no current, you see there's that 5 volts is going to be the same voltage at the base. Now you have a base to emitter 5 volts. That's impossible. So that's why it's not in off mode. Okay. So good choice. We assume it's in active. Now we have done it. It is active. That's fine. We finished the problem. Yeah. So this is the solution that was given to the problem. Now let's do one more. If I look in the circuit, it's a PNP. So by looking at PNP, current flows down from the emitter to split between base and a collector. Now, again, this thing is not going to be in off. Why? Because if it's off, like you can write this, if off, and then no current, right? No current anywhere. Off means no current anywhere. If no current anywhere, you see that VB will become 0, and VE will become 5 volts. So VEB equal to 5 volts. So that's not possible. So I just write down this one for you guys. If next time you want to write down yourself for another problem, you can do the same. If you assume it's off, there will be no current. If no current, the base voltage becomes 0, and emitter voltage becomes 5 volts. And you cannot have 5 volts from emitter to base for PNP. So therefore, it is not off. Okay. So now, if it's not in off, of course, we wouldn't know whether it's active or saturation mode. So we're going to do we're going to have to do one or another. So we can start with assumption like in active mode and to see what happens. And then of course you can also start. So if you look at here, you probably know it is in saturation, but if you start with saturation, it will be better because you're going to do one pass. But since we have done the other problems with the assumption of active mode, so we're going to do this same thing. So we're going to assume it's active. So we're assuming active. We know that VBE, actually VEB, because the PNP, so we have to be careful. It's what. Oops. So oops, what happened? VEB equal to 0.7 volts. I'm going to divide this into 3 columns so that I have enough space. So VEB is 0.7 volts. So therefore we have now the question here is that whether we want to start with the value of beta, because beta was not given. So if beta was not given, it's not easy to find the relation by considering how much IE and how much, let's write down. So this IE, IB, and IC. We wouldn't know VE, because we don't know the current in the branch of B. Now we can write a very complex equation to, if we know better, then we can solve for the three relations. We can find eventually the solution. But since beta is not given, so one of the idea to start this problem is to assume beta is infinity. So assuming beta infinity or very big means IB is 0. So that assumption you can start with. Of course, you can always come back to adjust it. So assume beta is infinity. So, and then assume beta is infinity. And then we'll have IB is equal to 0. If IB is 0, and then we have VB equal to 0.7. I mean, VB is equal to 0. And so therefore, VE equal to 0.7 volts. So the only thing that we come out with this assumption is to ignore VB, IB, to ignore IB, so that we can find the voltage at the base, and therefore we find the voltage at the emitter. So once we find the voltage at the emitter, we can find IE equal to 5 volts minus 0.7 divided by 1K. That gives you 4.3 milliamps. So now we can find IC is equal to IE. It's 4.3 because it's the active mode. Because IB is 0. That's because IB is 0. That's what we assume. So okay, so we find IC, IE 4.3. Finding IC already, you should be able to see because okay, we'll find VC is -5 plus 10K times IC, which 5 plus 10 times 4.3. So that's 43. That gives you 38 volts, which is not possible. So that's very important. So we start with an assumption of active mode and we find the current, we'll do that. Then we find, no, actually it's impossible because VC cannot be 38 volts, which is, it has to be between -5 and 5. So actually it has to be less than 0.7 by at least 0.3. So it has to be much lower than that value. So therefore it's not possible. So assumption is wrong, redo. So redoing this problem, we're going to assume so if we assume in saturation, we'll say VEC is going to be 0.2 volts. Okay. So the next, I think this is going to be a little bit tricky because if it is in saturation, IE and IC are no longer going to be the same. Remember, beta becomes smaller, right? So the way to do this problem, we probably should, because remember earlier we use this equation here, like IE equal to IC equal to, let's say in this case 5 minus 5 minus 0.2 divided by 1K plus 10K. Remember this kind of problem? Like we did this. Nothing. So therefore we shouldn't be using that equation. So let's then how are we going to do it? How are we going to do this? We can, let's see if I have space here. Yeah. So what we can is we can start by labeling the voltage at each node, and then we write the relations between the three currents. And therefore, from there, we should be able to solve. So if we number all the currents, we can find VB equal to IB times 10K. So the very first equation you can write. I don't know if you guys can see this clearly. So VB, the voltage at the base, is simply the current base. That's the current, VB. VB here. And then we can also write, so VC is a VE is VB plus 0.7. Okay, so VE is 0.7 above. VE is 0.7 above the VE is 0.7 above VB. Oops. So VE is 0.7 above VB, so therefore we find VB plus 0.7. Okay. The next, we'll find VC is VE minus 0.2, because it's saturation. Therefore, VC is VE minus 0.2, so we have another equation. And then we have, so by this point, we have how many variables? One variable, 2, 3, and 4. So we have 4 variables, but we only have 3 equations. So therefore, we still cannot solve for any of this because we got too many variables, more variables than our equations. So the next thing that we can find is we can start, it's not enough space anymore, but we can probably write on the next slide. So let's rewrite these equations here. So we have VB equal to 0.7 plus 10K times IB. And we have VE equal to VB plus 0.7. Then VC equal to VE minus 0.2. Did I say that? Yeah, minus 0.2. So we have that. But next thing is that we can start to look for current, because since now we know IE is going to be 5 volts minus VE divided by 1K. That's the top branch current. 5 minus VE divided by 1K gives you IE. And then we can find IC is going to be VC minus or plus 5 now divided by 10K. Okay, we get another equation. And then we have IE equal to IB plus IC. Okay, so now we're going to count how many? 1, 2, 3, 4, 5, 6 equations. We have 6 equations. How many variables do we have? 3 currents and 3 voltages. Yeah, we should be able to do it. It's just little, I mean, this is not really that difficult because every equation is only one and another variable. So for example, the second equation is VC equal to VE minus 0.2. So you have VE equal to VC plus 0.2. You plug in, you eliminate one variable, right? And then this equation, for example, you can eliminate one variable, but only the last one is if you plug everything into the last equation, you will be able to find all the stuff that you need. So finally, the solution is, yeah, I actually don't have the solution, but anyway, so I think the solution, what you find is, we call it beta F is IC over IB, and then it gives you 2.8. So this is the final solution. You find IC, and then you find the ratio between IC over IB. You can see it's a very small number. Instead of 100 or something, it's actually much smaller because it operates in the saturation region. Are we doing okay? Yeah. You mean, yeah?
On the last page.
Oh. What is that is, okay, yeah, good observation. What is that this transistor beta is pretty big, it's 30. So if you find that the beta is 2.8, which means it is in saturation. But in real life, you might find a BJT that has actually a beta of 2.8. So then you find a beta 2.8, it's actually not in saturation. It's actually in medium mode. So that's what it does say. So there's a big difference between beta and the actual saturation beta first. Yeah, it just tells you that the beta is not that small. So what it says that if you want a beta 2.8, and you compare it to that 30, yeah, it's much smaller than that. So it got to be in saturation. That's what it says. Okay. Okay, so 6.9. Okay, so we're gonna move on with the next one, 6.10. So this one looks a little bit more complex because it's no longer like a single branch. You got two branches. For this type of problem, there's an easy way, approximate way, and there's this hard way, which is more accurate way to do the problem. So probably, let me see how much space they have. Okay, so one easy way to do is to start assuming beta is very big, like infinity. Now, if you assume beta is infinity, so let's say maybe 1. So assume beta is infinity. If you assume beta infinity means there's no current in that from into the base. If no current in the base, so RB1, RB2 in series. Right? If it is in series, and you can find voltage at VB is equal to what? 15 divided by 100 plus 50 times 50. So that gives you 5 volts. So basically, what it says here. So once you have 5 volts, and then there's no current into the base, so you see what happens? Is that now you have the problem same as, so this problem goes like this. This problem goes like, so that's 5 volts. And then, so this, you look at this problem, is exactly the same as the one that we did before here. Not this one, but not this one, but this one, yeah. So it's exactly like this one, right? So there's not a lot to do. So that's one. But the more accurate way is that not going to assume beta infinity. So beta is actually is not infinity. So beta is 100. So beta is 100. And then still we have to do this problem. One way is to do it like direct way. Another one is to use node-dense analysis. Okay. Let's start with doing the problem using the direct direct method. A direct method says that if we do current here, we got IB, and I tell you this is going to be a little tricky because you will find a solution, but it's going to be like quite complex. Okay, so but we know that beta is 100, so therefore we're gonna do is we find we're gonna mark them. We see we and of course, just one more thing I forgot. You have to know whether it's in saturation or whether it's in active mode. But into either one, this is going to be like different procedures if you assume it's in saturation and active. So let's assume in active mode to start with. Assume in active mode. Okay. So assume active mode. Now we're going to find, let's call it IC, IE. So we have IC, IB, IE, and then we have, let's call it I1 and I2. And then we're going to have VB, VC, VE. So on this diagram, what I did, I marked them as each one of them. There were IC, IE, IB is 3 variable, and I1, I2, 2 more variable, and VC, VE, VB 6. So how many? 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 variables. Now, in order to solve that, you need 8 equations. You need 8 equations. But so equations are not that difficult. We can start with, for example, here, we can start IC equal to 15 minus VC divided by 5K, right? We can write 1, and we can find IE at the bottom equal to VE minus 0 divided by 3K. Again, another one. And then we write IE equal to IB plus IC. So we have another one. And then, so we have 3 equations now. But we have, so we have 8 variables. So it's not going to be easily solvable without digging further of the circuit. So the next thing that we can do is to look at VB and VE, the relation between VB and VE. So we know that VE equal to VB minus 0.7. So that's another equation we can find, right? Let's find it. The VE here is 0.7 was less than VB. So we find that one. Yeah, so the whole equation. Now we're going to write also I1. So I1 is going to be 15 minus VB divided by 100K. And we're going to write I2 as well. I2 is going to be VB divided by 50K. And then we're going to write one more equation is on this node, on the VB node. So you look at the VB node, I have 3 currents. And then I1 flows down, I2 flows down, IB goes in. So therefore you have one more equation is I1 equal to IB plus I2. Okay, so how many equations we have now? 7. We need one more equation, right? 2, 6, 7. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Maybe how many? Where do we find the additional equation? Oh, yeah. So, okay, sorry. We know that IC equal to beta times IB. That's the one that we kind of forget. It's not on the circuit. It's a property of the So now 8 equations. We should be able to solve for each of the variable, but certainly you might already see that, wow, that's a lot of work. Even equations is quite simple. but when you put them together, you plug in back and forth, and still, start to cause errors in the process. So because it's a little bit more complex to do, so the easier way to do this problem is by doing this node analysis or Devin's analysis per se. So for Devin's analysis, so let's look at the circuit of right. So this is a Devin's, this is a part of the circuit. And because for any circuit, we can make an equivalent circuit of Devin's. So remember, any circuit, we can represent circuit with a voltage source and a resistance. And then we call this RTH, we call this VTH. The only thing that you guys need to remember, how to do this. So this one, actually, if I do this one, this is what I have. So this is the ground. Really, that's the part of what I redraw is the part, the part not part of the BJT, but the biasing circuit, but biasing circuit on the. So for that, of course, they're here. We're going to connect like BJT later. So I'm looking at let me circle this one. So I'm going to look at this blue part. So you guys remember when you solve for Devin's equivalent circuit, how do you find the voltage? If you have anything inside, you would simply solve for the circuit, you'll find the open circuit voltage. That's what you find. So if you find an open circuit voltage, you find this VTH is simply 50 over 50 plus 100 times 15. That gives you 5 volts. And the next thing is to find RTH. So to find RTH, you would short the voltage source and open current source inside the black box, and then solve for the total resistance. Now, when you do that, when you short the voltage, you see RB1 and RB2 becomes, are you sure? Parallel, yeah, it's parallel connection, okay? So it's in parallel, so it becomes 50 over in parallel with 100. I think you get 33.3 kilo ohms. So you find that. So once you find that circuit, we can replace the circuit. So number 2, so we replace the circuit with this, with the voltage and so this is 5 volts, this is 33.3K, and this is 5K, this 3K, and this is 15 volts, and this is ground, and this is ground. So we find this equivalent circuit. So this part is a Devin's equivalent. Let me circle that with a blue circle. So this part is the Devin's equivalent circuit. Okay, so now we find the circuit 5 volts, 33, and 5K here. See, you see this problem? We have done that before. We have done that before already. You can start to write like the equations, but will be much simpler than the one that we tried to do on a previous slide. You can do that. Okay. So I'm going to leave the rest for you guys to do because we have done that before. We're not going to repeat the same procedures we have done before. Okay. Now, one thing I want to emphasize at this point, of course, you still have to assume whether it's in saturation or whether it's in active mode, and you do the problem. And when something is wrong, you have to redo it. So there's no shortcut for this process. You just have to start with one assumption and do another. So this assumption, in this case, it was assuming this in active mode, and you solve for the voltages, currents, and you find actually it is in active mode. So we find the voltages and currents at each terminal, right? Okay, so I think we are going to run our last problem. When you look at this, you might say, oh my God, this has too many components in the circuit, which is true. But you look at what the circuit is giving you is actually very simple. It gives you beta is infinity. So beta infinity means alpha is 1, which means IE and IC are the same. Remember, right? Do you guys remember all the equations? So IC equal to beta times IB, right? If beta is infinity, if beta is infinity, IB is 0. And also you remember IE equal to IC plus IB. So if beta is infinity, which means IE equal to IC. So it's once that condition is given, your circuit is very simple to start with, because what you're looking at is there's no current here, there's no current here. But of course, this is often how engineers start with their design. Because in the initial design, IB is so small, just let's neglect it and do the big picture. But once the circuit design is done, you will have to go back to the actual circuit by using the actual beta and alpha to solve the problem. It can be done because you can always write the same number of equations as the same number of variables based on circuit configuration. But it's just, I can tell you, it's tedious. Because with that one transistor on the previous example had like 80 equations. But for this like double transistor, you're probably going to have more than 10 equations. So it's going to be tedious. It's not easy to do, but you can do it. So now knowing that beta is infinity, knowing that current into each of the base is 0, it greatly simplifies the problem. Like in the beginning, for example, if current going into Q1 is 0, can you find the voltage at the base of Q1? Easily. Just by observation, you probably already know how much voltage is that? 5. So VB1 is 5 volts. Why? Because it's 15 volts divided by these two resistors, right? So if that is 5 volts, you can easily find here the VBE, right? 0.7. Now, what I'm doing here is I'm going to assume them all in active mode, okay? For circuit like this, most likely they're in active mode. Otherwise, the design is probably wrong. So, okay, so if VB1, that's because VB1 is 0.7, you can find VE1. How much VE1? Guys, tell me. 4.3. Because it's 5 minus that 0.3 across that BE junction. Okay, so if VE1 is 4.3, how much current can you find on IE1? It will be 4.3 divided by that 3K resistance. So it's like 1.23 milliamps. Okay, so let's say 1, 2, 3, 4. Now let's do 5. So if we find IE1, because beta is infinity, so we'll know IC1 is going to be same as IE1 is going to be that 1.23 milliamps. So now let's together find VC1. Can you find VC1 now? Well, VC1 is going to be the 15 volts minus RC1 times IC1. And RC1 is 5, and IC1 is 1.23, so it's 1.23 times 5, it's like more like 6 volts, so almost 9 volts. So VC1 is almost 9 volts. Like you guys can get an accurate number. So now you find VC1, the Q2. Q2 is what transistor? What type? Q2 is PNP. Q2 is PNP means we should be able to find VEB2 is 0.7 volts. VEB2 0.7. Now we see what so we can find VE2. So number 8, we will find VE2 is equal to VC1 plus VEB2. So if that's 9, now you get 9.7, right? So on number 9, we can find IE2, because IE2 is 15 minus VE2 divided by RE2. So you find that current. Now, number 10 will be IC2 equal to IE2, because beta again is infinity, right? So IC2, IE2. Now find IC2 already. You can easily find VC2. You guys can find VC2. Let's write together. How much is VC2 in terms of equation? It is simply the voltage drop across RC2, right? Because the bottom is ground. So it's equal to IC2 times RC2. So by plugging the numbers, now you can find VC2. Yeah. VC2, IC2 times RC2. Now, of course, if you guys want to do one more step, you want to find like a VCE1 and find VEC2. The reason we want to do that is, let me probably make a little bit more space here, because we don't need that equation anymore. We can find VCE1 is VC1 minus VE1 to see how much that is. So where VC1 is 9 volts and VE1 is how much? VE1 4.7. So that is larger than 0.3, which means it's active mode. You can also find VEC2, which is VE2 minus VC2, and plug in the numbers. You can find the number, which also has to be larger than 0.3 volts. So to make it in active mode. Now, if you find any of these numbers, that's there's just one more thing I want to mention there. Sometimes when you do the problem, you made a mistake in the process. So that, like, for example, solution actually is correct. But if in the middle somewhere, let's say you made a mistake, instead of plugging a 15, you plug a 10, right? And then the number will be wrong. And the number wrong, the number is wrong. And then up here you find, oh no, actually, this is not, it's less than 0.3. And you say, oh, it's not in active mode. Go back to redo it. And you go back to redo it, you find, well, it's also not in saturation mode. That right, but actually you did it wrong here. So you would say, if you go back, you find your other assumption is also not correct, you must have done some mistakes in the process. You would have to carefully look, okay, where did I make a mistake? This transistor has to work in one or another mode. It cannot be in the transition mode. It cannot be in both modes or not in both modes. It has to be in one mode, cannot be in both modes. Okay. So I think we can finally give you the solution here. How we did it? Oh, actually, no. Okay. So what we did was assuming beta is infinity, and we find all the solutions. That is true if beta is infinity. If beta is not infinity, the solution would have been off just a little bit. But how do we do that? So by observing this circuit, you will probably know that the way to do this, if I'm going to redraw the circuit over here, so you guys know what I'm talking about. This is the negative ground, 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 ground. So this is the original circuit. Remember from example 6.10, when we have two resistance at the base, what did we do? We do derivatives. So this circuit initially, at least we would simplify this circuit to now this will be 5 volts, okay? It's not going to be 15 volts. So this is 15 volts. And here, so at least we can simplify the previous part on here. Now, when we did this, we can do this part. We can do the first part by neglecting the second part, by solving that circuit. Now, once you do that, like you cut off this one, we cut off that, and we do this circuit like we have done before, we can do that. Once you find the solution, you'll find, well, there is something connected. So the only thing that is wrong was that there's actually a current going through this way, there's a current going this way. So IE1 is actually going to be IC1 plus IB1, then also plus IB2. So this is the extra term. This extra term flowing into this one. So that's the one we have to get back on to find the actual solution. We solve for this part as well. Now, ideally, you can write all like 10 plus equations, and then you can solve for each of the variable. You'll be okay. But again, the process can be tedious. So therefore, I'm probably not going to get you guys to that. At least in the exam, you wouldn't do that because that might take you guys half hour, or maybe most of the time just do one problem. So we're going to have a lot of assumptions, and you guys can do not that difficult a problem. But this is what the final solution look like if we actually did it, not assuming beta infinity, with actual beta is 100, and all the currents and voltage, everything like we write 10 plus equation. The illustration really tells you, look at current, how small. How much current point here? 1.29. And the difference is less than 1%. So in reality, if you did assume beta is 100, you wouldn't make a big mistake. It's only 1% off. It's not a big deal, right? Here, 2.75. This is 0.02. So that's voltage-wise, going to be off too much. But anyway, so right here, of course, bit of currents up close. So therefore, that makes a big difference. But that has a change over there. Okay. So that is what we have. Basically, I'm going to skip to the next question. Probably my TA next yeah. So this Thursday and next Tuesday, like my TA is going to do more examples for you guys. So if you guys want to have a good score, come to those lectures. It's going to help you. Okay. She's going to do a lot of examples. Some of them will be very similar to the exams. This is another problem that look like a little bit like problematic because you got two transistors, you get one on the top and one at the bottom, and then they were connected, and then the base was also connected, and then the emitter also connected. So the emitter of the PNP and NPN that's connected. They want to ask you to look for the currents and voltage in each of these transistors. So basically, once you look at the circuit, well, you can start looking at which transistor is conducting or not conducting, or both conducting, both off. So this is a little bit of work, just looking at how to analyze the transistor. So like if we assume Q1 conducting. So if you assume what you can do is you can find VBE1. So from here, you can find VBE1 is equal to 0.7 volts. So let's call this VO. So guys, if VBE1 is 5 volts, how much is VO? Now, in this case, we are assuming beta is infinity, okay? Just simplify the problem. You see what happens. So now, because beta, so you got 5 volts here, and you got a 5 volts here. So now VB1 is 0.7. So how much is VO? VO is going to be 5 minus 0.7. It's going to be 4.3 volts. Okay, so 4.3. So if VO is 4.3, how much is VEB2? VEB2 is VO minus 5 volts. It's minus 0.7 volts. So in this case, Q2 is off. The current flows from this one all the way here. Does it make sense for you guys? I assume Q1 is on. Well, this time I don't care whether it's saturation or active yet. I'm just saying which one is on. So Q1 is on. So we have VBE1 from base to emitter is 0.7. So we have VO is base voltage minus 0.7, so that's 4.3. Okay, so VO is 4.3. From VO to VB2, or from base of Q2, that is going to be like VO minus 5 volts because the base is 5. So you get minus 0.7. VEB2 minus 0.7 means it is in off mode. So this looks like okay. Now you might say, well, I don't trust you. What happens if I assume Q2 is on? Can I do that? Okay. Well, so seems to be okay. At least I would say it seems okay, right? I cannot convince myself otherwise because everything seems to be logic. Now we're going to assume Q2 is, or let's say assume Q1 is off, right? So if we assume Q1 is off, then probably not going to make sense because off doesn't tell you any information. So I'm going to assume Q2 on. See what happens. Q2 is on. Now, if I assume Q2 is on, let's say how much is VO? So VEB2 is 0.7 volts. So VO is going to be 5 plus 0.7, that gives you 5.7 volts. So if we is 5.7 volts, yeah, so we Q1, we BE1 is going to be 5 minus 5 minus 5.7 gives you minus 0.7 volts. Okay. Now you might say, well, VBE1 is negative, so VBE, so Q1 is going to be off. Everything seems to be logic. Is right? But I got in this dilemma. Conducting, it was good. I think Q2 conducting, also good. It cannot be true. As I said, you cannot be either this one or this one. You have to be one or the other. You cannot be both. What's going on? I want you guys to look carefully. With the first assumption, did you see the current flow direction that I marked? In the first case, in the top case, the current would flow from 5 volts to Q1 and then to 1K resistors. It goes down. Everything seems to be okay. But for the second case, what happens? If VO is 5.7, if VO is 5.7, what happens to the current to the 1K resistance? That's the problem. So in the second case, you have a current flowing down this way. Where would that current come from? Because I assume Q1 is off, no current there. Now I assume Q2 is on, but Q2 actually conducts current also down. You can't have current both going down. You have to, maybe if Q2 can conduct current upwards, maybe okay, but no, it's not. So therefore, our second assumption is wrong. You cannot have current flowing upwards in Q2. It's a transistor, it's a BJT. BJT can only conduct current on the PNP, can only conduct current from emitter to that. So that's why this assumption is wrong, only the top assumption is right. Okay. So this is very tricky. Sometimes you know, I got both of them right. I don't know what to do. Well, because we didn't observe carefully what happens if there's no 1K resistance, this would have been in trouble because both states could be right. Okay. But that generally would not happen. It can only go to one state or another. So in the future, by moving on in like 1.5 weeks, well, after, actually 2 weeks after the break, we're going to move on to chapter 7. We're going to talk a lot about common base and other things and common emitters. So we're going to skip those later on. And also, one more concept is the temperature change is going to impact the performance. So that's something just keep in mind when you do your design. Okay. So that's all for today. Well, wish you guys good luck.
Yeah.
Thank you.
Okay.